Hi, I'm Taegeon. I'm from Seoul National University. In this presentation, I'm going to talk about Pluto, high-performance IoT-aware stream processing. This work collaborated with Gyewon Lee and my advisor, Byung-Gon Chun. Today, various data streams are generated from diverse IoT devices and processed in backend servers. Each IoT data stream has low input rate. For example, one temperature event is generated per second from a temperature IoT sensor. Due to the large number of various IoT data streams, a new stream query workload emerges. Different from the traditional big stream query, which processes a huge volume of data, an IoT stream query processes a small amount of IoT data streams related to certain IoT devices. And the IoT stream queries are created for end users via mobile or web applications developed by application developers. For example, at home, an IoT stream query can process the current room temperature data and automatically adjust the air conditioner cooling temperature in the room. As various IoT applications are developed and many end users use the application, a large number of small IoT stream queries can be executed on backend servers. Therefore, it is important to efficiently process as many small IoT stream queries as possible in a node to reduce the required number of machines and maintenance costs, which is the focus of this work. However, as existing stream processing systems are optimized for processing individual big stream queries, they have limitations in handling a large number of small IoT stream queries due to inefficient query submission and execution layer. To explain the limitation, we first illustrate how they submit a stream query. Usually, a stream query is represented as direct cyclic graph, and the query has user-defined functions and codes which are written by application developers. So to submit a query, both of the DAG information and the code are sent to and uploaded to the driver, and the code is loaded to the executor. However, if a large number of queries are submitted at a time, the tightly coupled code and query submission path becomes the bottleneck because a huge amount of code are unloaded and registered to the driver and loaded to the executor whenever queries are submitted. Second, to execute a query in the executor, existing systems allocate system resources separately for each query. For example, they separately create network connections, load code, and create threads for each query. However, if a large number of small IoT stream queries are executed, the system resources easily become the bottleneck due to the separate resource allocation. To address these limitations, we designed Pluto, a new stream processing system optimized for handling a large number of small IoT stream queries. The key idea is to optimize not only the execution layer, but also the query submission layer by decoupling the query submission and code registration and harnessing the characteristics of small IoT stream queries. In Pluto, the end-to-end query execution consists of three phases. The first phase is code registration phase, where application developers register their application code, such as user-defined functions. The second phase is query submission phase, where the actual query is submitted without code to reduce query submission overhead. The third phase is query execution phase, where many queries are executed on the Pluto's execution layer with optimization techniques. Here, we show the overview of code registration and query submission in Pluto. First, application developers write application code with Pluto's client API and submit the code to the Pluto's code manager. The code manager then checks whether the submitted code is unique or not and stores the code into the code storage and returns a unique code identifier if the submitted code is new one. Once the code is registered, developers encode the code identifier in the submission of stream queries. So queries are submitted with the code identifier. By decoupling the code registration and query submission path, the same code is registered and uploaded only once, and the actual codes are not sent during the query submission. In addition, by directly sending queries to the worker, Pluto simplifies the query submission path and reduces the query submission overhead. The paper contains the detail of the code registration and query submission API, so please see the paper if you're interested in. In the execution layer, Pluto efficiently executes many IoT stream queries by sharing system resources as much as possible. In detail, we apply various optimization techniques. First, Pluto shares network connections across queries that connect to the same message broker. As each IoT data stream has low input rate, multiple IoT data streams can be managed by the same message broker. Pluto exploits these characteristics to share network connections across queries. Second, Pluto shares codes across queries by being aware of the code identifier. When multiple IoT stream queries are submitted from the same IoT application, they have the same code identifier. Pluto uses this information to share codes across queries in execution. Finally, Pluto shares threads with the thread pool model and locality-aware scheduling. To efficiently execute many stream queries in a thread, Pluto groups queries that refer to the same code and executes their events consecutively in a thread to exploit code cache locality. Now we show the evaluation result. Our evaluation is performed on a 24-core NUMA machine, and we emulate IoT workloads with real-world dataset and applications. We measure the maximum number of small IoT stream queries that can be processed in the machine. For baseline, we use Storm, PipelineDB, and Flink, which are popular stream processing systems and stream databases. This is the evaluation result. As you can see, Pluto outperforms other stream processing systems by orders of magnitude due to the efficient query submission and execution layer. To show which factors contribute to the performance of Pluto, we break down the performance. Here, TPQ is an optimized Flink where query submission and code registration is decoupled. Therefore, comparing it with Flink shows the benefit of decoupling of code and query submission. Comparing TPQN with TPQ shows the benefit of network connection sharing. And comparing TPQ plus NC with TPQ plus N shows the benefit of code sharing. Finally, comparing Pluto with TPQ plus NC shows the benefit of thread pool model with locality-aware processing. In conclusion, to efficiently handle a large number of small IoT stream queries, we designed Pluto by optimizing both query submission and execution layer. Our evaluations show that Pluto improved system throughput by orders of magnitude compared to existing stream processing systems. This is the end of the slide. Thank you for listening.